Hello everyone. Uh, Let us continue with module number 3, wherein I have started with beams and shafts. So in beams, I have completed the stiffness matrix of beam, safe functions of beam element, and load vector due to UDL, and few numericals related to beams what I have discussed in the previous lecture. So let us today start with the torsion of shaft. So in the torsion of shaft, uh, it is required to consider the finite element formulation of shaft element. So here it is considered a circular shaft of length dx, and it is considered in xy direction and is subjected to a twisting moment or torque of magnitude t. The diameter of this circular shaft is d, and the modulus of rigidity is mentioned in terms of g. So, due to the application of a twisting moment or torque, so there will be angle of twist of the shaft, and the change in angular position is represented by gamma max, that is maximum shear strain in case of the circular shaft. So let us first try to have the uh, the finite element formulation or its a discretization process. So here it is considered as node 1, and at this location it is node 2. So it is subjected to a twisting moment or torque at node number 1, which is maybe a fixed end, and where I am considering it as the twisting moment as T1, and the corresponding angle of twist at that location is theta 1. And at node number 2, the angle of twist is T2, the torque applied is T2, and the corresponding angle of twist is theta 2. So here T1 and T2 are the end torques corresponding to node 1 and node 2, and theta 1 and theta 2 are considered as the angle of twist or end twist at node number 1 and 2 respectively. So it is we can derive the safe function related to the a shaft subjected to twisting moment or torque in a similar way as that of the bar subjected to an axial force. So here there is a simple shaft element which is subjected to torque instead of force. So in order to derive its safe function, let us consider the linear angle of twist variation along x direction is represented by a polynomial theta is equals to a1 plus of a2x. Now we have to use the boundary conditions of node 1 and node 2 in order to calculate the value of a1 and a2 or the generalized coordinate. And once you calculate that, what we will get exactly is theta is equals to the safe function n1 n2 into the displacement vector in terms of angle of twist as theta 1 and theta 2. So this will get exactly as that of the bar subjected to force. Instead of force value, here we have the angle of torque value, and instead of displacement in terms of u or q, in case of shaft subjected to torque, we have the angle of twist represented by theta. So therefore, in global coordinate system, the safe function n1 will be equals to x2 minus of x divided by x2 minus of x1, and n2 is equals to x minus of x1 divided by x2 minus of x1. So the relationship between shear strain, gamma, and angle of twist theta can be obtained by considering the torsional deformation of the bar segment as shown in figure. Assume all radial lines such as OA remain straight during angle of twist. So these are some assumptions. So I'll just have the review of this. There is a circular shaft which is considered in x direction subjected to torque T. Due to the application of torque, there will be change in angular position in terms of angle of twist. So this is a link element or shaft element which is considered in x direction, having two nodes, node 1 and 2, subjected to the torques T1 and T2 corresponding to node 1 and 2, and the corresponding angle of twist are theta 1 and theta 2 with respect to node 1 and node 2. So if you apply the, if you consider the displacement function in terms of angle of twist for this shaft element, and if you apply the boundary conditions, of node 1 and node 2, we will get the safe function similar to the bar subjected to force, and where we get n1 as x2 minus of x divided by x2 minus of x1, and n2 as x minus of x1 divided by x2 minus of x1. So when you look at this figure, the gamma max, so the gamma max is the arc length of this AB. The arc length of AB will be equals to the arc length of AB is given by gamma max into the distance of dx, or it is radius into d theta, the angle of twist, so which is d theta. So therefore, gamma max can be written as r into d theta by dx, and r into d theta by dx can be written as after at any position we can write it as r by L into theta 2 minus of theta 1. So we know that modulus of rigidity, G, is the ratio of shear stress to shear strain within the elastic limit, and therefore we also know the torsional equation, which is T by J is equals to tau by R. So T can be written as tau J by R. So where J is polar moment of inertia, and therefore T can be written as Gj by L into theta 2 minus of theta 1. So substituting equation 1 and 2 in equation number 3, so what we'll get is Gj by L into theta 2 minus of theta 1. So when you see the figure, so at node 1 T is minus T1. So at node 1, uh, looking at the figure once again, at node 1, the torque is acting in anti-clockwise direction, and in case of node 2, it is acting in clockwise direction. So at node number 1, T is considered as minus T1, and at node number 2, therefore T1 is equals to Gj by L theta 1 minus of theta 2 when you substitute T as minus T1, and at node number T2, it is Gj by L theta 2 minus of theta 1. You can expand this, or else you can write in terms of matrix form. So left side from equation 4 and 5 we have T1 and T2, and the common factor is Gj by L, and the coefficients of theta 1 and theta 2 are 1 minus 1 minus 1 1. So this Gj by L into the matrix of 1 minus 1 minus 1 1 is the stiffness matrix for the torsional bar. So where K is called as the stiffness matrix for the torsional bar. So in this way, we can have the formulation of the shaft subjected to torque. First of all, we can have the shape functions of the member subjected to twisting moment or torque, which is exactly similar to the bar subjected to force. And in global coordinates, we get n1 as x2 minus of x divided by x2 minus of x1, and n2 will get it as x minus of x1 divided by x2 minus of x1. And when to have the stiffness matrix of the shaft subjected to torque, first of all, we have calculated the arc length, and we have written the gamma max. Gamma max is just given by r into d theta, so which is equals to r into d theta by dx. And at any location, we can calculate the gamma, that is shearing strain, which can be expressed as r by L into theta 2 minus of theta 1. So from this simple calculations, or by applying these simple relations, we can get the stiffness matrix for a member subjected to twisting moment or torque, and that stiffness matrix K is given by Gj by L in the matrix of 1 minus 1 minus 1 1, where G is modulus of rigidity, J is polar moment of inertia, and L is length of the member. So let us start with the numericals related to the torsion or shaft subjected to torque. So there is a stepped bar or stepped shaft having the circular cross section, and they are subjected to a torque of 1 kilonewton meter at the free end, and a torque of 3 kilonewton per meter at the change of cross section. So the diameter of the first step is 100 mm, diameter of the second step is 50 mm, the length of the first step is 200 mm, and length of the second step is 400 mm. So it is asked to calculate the angle of twist and also the shear stresses in the member. It is asked to consider E as 2 into 10 power 5 Newton per mm square, and modulus of rigidity G as 7 into 10 power 4 Newton per mm square. So the first step is to have the formulation of the given problem continuum. in terms of elements and nodes. So this is considered 100 shaft is considered as element 1 and 50 shaft as element 2. So this has node 1, left hand as node 1. This at the center it is considered as node 2, and this hand it is node number 3. It is assumed that the torque acting at node 1 is T1 and the corresponding angle of twist is theta 1. The torque acting at node number 2 is T2 and corresponding angle of twist is theta 2. The torque acting at node number 3 is T3 and corresponding angle of twist is theta 3. So this is the first step in finite element formulation. The second step is to have the stiffness matrix of individual element. There are two elements in the problem. So to have the elemental stiffness matrix of the first element, so K1 is equals to G1 J1 by L1 in the matrix of 1 minus 1 minus 1 1. We have the G value which is 7 into 10 power 4 and into J1 value 9.82 into 10 power 6 divided by 200, which is in terms of millimeter, into 1 minus 1 minus 1 1. So when you calculate this, we'll get the common as 10 power 9 in the matrix of 3.44 minus 3.44 minus 3.44 plus 3.44. So here we can have the stiffness matrix of the second element. We have the same value of G and different value of J as the cross section is different, and we will get it as a 10 power 9 in the matrix of 0.107 minus 0.107 minus 0.107 and plus 0.107. The third step is to have the global stiffness matrix, that is assembly of the two stiffness matrices, which is therefore K is equals to K1 plus of K2, and globally as there are three nodes with 3 degree of freedom in terms of theta 1, theta 2, theta 3. So consider a blank 3 by 3 matrix, so wherein we have 10 power 9 as common corresponding to theta 1, theta 2, theta 3. In column also corresponding to theta 1, theta 2, theta 3. Write the coefficients. So that is 1 cross 1 element or theta 1 cross 2, theta 1 element is 3.44. Theta 2 cross theta 1 is minus 3.44 and theta 3 cross theta 1 is 0. Similarly, theta 1 cross theta 2 cross theta 2, it is at two locations, which is 0.344, sorry, 3.44 and 0.107, which need to be added, and the resultant value is 3.547. And rest of the matrix is corresponds to element 2, which is minus 0.107. Here also it is minus 0.107 and plus 0.107. So the load vector corresponding to node 1, node 2, node 3 can be written as T is equals to T1, T2, T3, T3, and there is no load at node number 1, which is completely fixed. At node number 2 we have T2, and at node number 3 it is in terms of T3. So it is used as it is in terms of kilonewton meter. Torque is used in terms of kilonewton meter. So it is 0, value of T2 is 3 kilonewton meter, T3 is 1 kilonewton meter. So the next step is to use the overall equilibrium equation, that is formulation of overall equilibrium equation, which is K into theta is equals to T. So therefore, where K is global stiffness matrix corresponding to step the shaft, theta is global displacement vector in terms of angle of twist, and T is global load vector in terms of torque. So as theta 1 is 0, of course, as it is completely fixed. So therefore, eliminating the corresponding row and column. So the remaining matrix is written here after elimination method, and after elimination we get, after solving, theta 2 as 1.162 into 10 power minus 9 radian and theta 3 as 1.050 into 10 power minus 8 radian. So we also know that modulus of rigidity is tau by gamma, which is shear stress by shear strain, and we also know that T1 as Gj by L in the matrix of theta 1 minus of theta 2. So with these two equations and the torsion equation, we can write it tau is equals to Gr by L into theta 1 minus of theta 2. We have the value of G, we have the value of R, so we can calculate the stress value, shear stress value in member 1 and also in member 2, that is element 1 and element 2. And when you substitute the value of theta 1 and theta 2, G and R, we will get the value of tau 1 as 20.3 Newton per meter square and tau 2 as 40.85 Newton per meter square. So similar to this, the second problem, it is a uniform shaft subjected to 1 kilonewton meter and 1.5 kilonewton meter twisting moments are torque at two different locations. So we have the length of the first member AB as 2 meter and BC as 1 meter and CD as 1 meter. So we can calculate the polar moment of inertia as J. It is a uniform bar which is pi d to the power of 4 by 32. We know the diameter of the member as 50 mm. We can calculate the polar moment of inertia here. So once we have the value of polar moment of inertia, we can go for calculating the stiffness values of element 1, element 2 and element 3. So we have the stiffness matrix as Gj by L in the matrix of 1 minus 1 minus 1 1. So we can substitute the given values of G, J and L for element 1, element 2, element 3. And in the next step we can add all the three stiffness matrices. We can form the load vector T1, T2, T3, T4 corresponding to node 1, 2, 3, 4. And we have load in terms of torque at node number 1 and node number 2 and node number 3 as 1 kilonewton meter and 1.5 kilonewton meter. Node 1 and node 4 are completely fixed, so therefore the torque acting at node 1 and node 2 are equals to 0. And when you form the equilibrium equation, which is K into theta is equals to T, global stiffness matrix of shaft, global displacement factor in terms of angle of twist, and global the force factor in terms of twisting moment or torque. So here as node 1 and node 2 are completely fixed, theta 1 and theta 2 will be equals to 0. And after elimination, we get 2 by 2 matrix, which can be solved for the corresponding angle of twist of node 2 and node 3. We will get at theta 2 and theta 3. So we can also calculate the stresses tau 1, tau 2, tau 3 in the same way as that of the previous problem. So like this, all the problems related to torsion can be solved. Thank you very much for listening the